So we're going to talk about Boyce Codd Normal Form. This is a very interesting normal form because it goes first, second, third, and then it will go to fourth. And Boyce Codd is somewhere in between third and fourth. It's often called the 3.5 normal form. But Boyce Codd is kind of weird, doesn't come into play a lot, but it comes into play to sort of solve the problems that second normal form and third normal form cannot solve. It's almost like a third normal form addendum. So we're going to talk about this. We're going to go through its definition and we're going to practice some Boyce Codd. So a little history around normalization. The normal forms, the first three that we've studied, were created by Edgar Codd, who in 1970 talked about normalization. It was not called first normal form in 1970 because there was only one normal form. But then in 1971, E.F. Codd expanded and added in 2NF and 3NF. Now, the most important thing to realize is that these normalization rules are very important. But if you design tables well and you follow the rules of transformation from ER and EER diagrams, you're very much likely to be in a third normal form on your first attempt. So this work was primarily done at IBM, and after a few years they realized that the existing first normal form, second normal form, and third normal form did not fully normalize data. And they designed a new normal form called the Boyce Codd Normal Form in 1974. This was developed by E.F. Codd, and he partnered with Raymond Boyce, who was one of the persons who co-developed the SQL language. Sadly, Boyce died at age 27 soon after this article was published. But what they said was that the improvements needed to happen over the second and third normal forms. They found cases where those rules did not normalize the data fully. And as they mentioned, these improvements remove the somewhat arbitrary distinctions drawn between prime and non-prime attributes. And you've realized that when we look at all the candidate keys, we reduce the number of non-prime attributes. And sometimes those prime attributes need to be removed from the table and placed into their own table. But second and third normal form does not allow for this. So Boyce Codd Normal Form was born. The real loophole of second and third normal form occur in very special cases. They occur in cases where your table has multiple composite candidate keys, which doesn't happen all the time. And when those multiple candidate keys have at least one common attribute. So it's a very specific set of circumstances that cause second normal form and third normal form to fail. And this is what those circumstances are. But the Boyce Codd normal form will address this. So this is the actual definition of Boyce Codd as written in 1974. And it says a relation R, or a table R, is in third normal form if it is in first normal form, and for every attribute collection C of R, which is a subset of the fields, if any attribute not in C is functionally dependent on C, then all attributes in R are functionally dependent on C. Now, that's a hard definition to wrap your head around. We will try to work it through. One thing is, in their paper, they talk about this being third normal form, but as things happen, the third normal form definition was already well entrenched and did not change. And so the words you read above became referred to as the Boyce Codd normal form. Notice one thing about this definition, which I grant is hard to read. The definition does not include non-prime attributes. You don't see those words anywhere. So for those of you who want to follow this, and you don't have to, here's the relation R, and this happens to be the table that we saw before with the invoice ID, the invoice sequence, the item description, and the invoice number. Part of the problem with this was that we had two candidate keys with an overlapping field. We had the invoice ID and the invoice sequence, but we also had the invoice sequence and the invoice number. So we had exactly the set of circumstances that Boyce and Codd were trying to avoid. So mathematically, we can show it on the right-hand side. R is going to be this table. We'll make C be the invoice ID. Therefore, the invoice number is not in C. And then we have this condition that C functionally determines the invoice number. Now, we also have the inverse of this. The invoice number also functionally determines C, but we're not going to focus on that. But once we have this state, we can see that not all attributes are functionally dependent on C. So, for example, the item description. The item description is not dependent on the invoice ID, but rather it is dependent on the combination of the full key, the invoice ID plus the invoice sequence. So this brings the table out of Boyce Codd Normal Form. I want to bring you to a simpler definition of Boyce Codd Normal Form that's easier to apply. But in order for me to do that, we have to go back and we have to remember functional dependencies. And specifically the definition of that, a set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. You may recall this from previous lectures. And then also, please remember that when you write them like this, X determines Y. X is the determinant, and Y becomes the determined. One more little thing we want to talk about. In the world of functional dependencies, there are two kinds. There are trivial functional dependencies, and there are non-trivial functional dependencies. We're going to only talk about non-trivial functional dependencies. But let me explain what they are. So here you can see that the zip code functionally determines the city. We expect that. But look, it's almost a unity operation. The zip code also functionally determines itself. Because if I know the zip code, I know the zip code. We never really write functional dependencies that are trivial. They're not that much used to us. So what we're used to is something like this, where the zip code functionally determines the city, and we're not going to repeat that the zip code determines itself. So from now on in this lecture, whenever we speak about functional dependencies, we're going to consider those to be the non-trivial ones. I'm not going to keep saying non-trivial. All right. Let's move on and find this easier definition of Boyce Codd. And here it is. A table is in Boyce Codd Normal Form if it is in third normal form and if every determinant is a candidate key. So what this means for Boyce Codd is you've got to identify all of the functional dependencies. And if the left-hand side, the determinant, is one of the candidate keys of the table, then we're all good. But if we can find a functional dependency where the left-hand side, the determinant, is not a candidate key, then we're out of Boyce Codd. The way to describe this is we're going to talk about good functional dependencies and bad ones. The good functional dependencies, X is going to be the candidate key, and the bad ones is when X is not the candidate key. So now that we see this, what are the functional dependencies? Well, we know that the invoice ID and the invoice sequence, that determines the item description. That's a good functional dependency because invoice ID and invoice sequence is a candidate key. But we have another functional dependency. We know that the invoice ID functionally determines the invoice number. We also know that the invoice number functionally determines the invoice ID. So it's a reciprocal functional dependency. But nonetheless, Neither one of those, neither the invoice ID nor the invoice number, the left-hand sides, the determinants, they're not candidate keys. That functional dependency does not belong in this table, and the table is not in Boyce Codd Normal Form. Back in the 2NF lecture, we looked at this, and we talked about vendors and invoices, and we had said that this was the minimum second normal form representation. Your book did not show that as a 2NF. The Murac textbook actually showed the bottom depiction as 2NF, and it is. But the top representation is the minimal 2NF. The smallest number of changes you'd have to make. Once we apply the Boyce Codd Normal Form and we realize we have a trouble with this functional dependency right here, we pull it out of this table and we can actually put it into the invoice ID vendor name. We built this table when we normalized the second normal form. And so if you notice, in the Boyce Codd Normal Form representation, now we have the invoice number, the vendor name, all associated with the invoice ID. So these functional dependencies now live in this table. What your textbook did and Murac did was they actually took it to Boyce Codd Normal Form in one step. And once you get good at normalization, you might be able to do that kind of thing. But we wanted to understand what 2NF required and what Boyce Codd Normal Form fixes. And so Boyce Codd Normal Form fixes this particular loophole that affected our vendors and invoices. As if things weren't crazy enough with the Boyce Codd Normal Form, in 1982, Carlo Zanillo proposed another normal form called the Elemental Key Normal Form. This one comes in between third normal form and Boyce Codd Normal Form. But frankly, no one really adopted it. It's out there, but no one really uses it. We're not going to discuss it. We already have this intermediate normal form called the Boyce Codd Normal Form. Who needs another one? This is a very important slide that I like to keep handy. It's the way to go through first normal form, second normal form, third normal form, and Boyce Codd. And it has all of the definitions that you need in order to normalize to Boyce Codd. It also has a cool alternate definition of third normal form. Every non-key attribute must provide a fact about the key, the whole key, and nothing but the key. So help me Codd. Well, at least I found that funny.